Okay, students, this is our last video on applications of derivatives. So what I'd like you to do with this one is, after we've read the question out, I'd like you to try each of the different steps before I actually do it myself. So in other words, I'm going to ask you to draw the diagram first. So you pause the video, have a go, and then check your answer. Anyhow, let's get started. A rectangular sheet of tin plate measures 24 centimeters by 18 centimeters. Squares are cut out of each corner, and the flaps are turned up to form an open box. So hopefully you have in your mind a picture of this flat plate. You cut out, with a pair of tin snips, you cut out squares of equal size from each corner, and then you can fold up the flaps, and you get a box that's open on top. Now, depending on the size of the squares you cut out, the volume is going to be different. So your problem is, can you find out what size the squares should be to give the maximum volume? Okay, step one. Could you go ahead and try to draw the diagram for this? Don't forget to include all of the relevant measurements, and anything that you don't know, make sure you use a variable for that. Okay, let's see how you went. So here's my diagram. So there's the piece of tin with the corners cut out. So the total piece of tin is 24 centimeters. The width is 18 centimeters. I don't know how big the size of the squares should be, so I just called that X. So that's X and that's X. Same with all the other dimensions in the four corners. They're all X. That means the length of the base of the rectangular prism is 24, take 2x, and the width is 18, take 2x, and the height of the prism is going to be x. So that's what you should have come up with, something similar to that for step number one. Okay, let's come up with an equation for the volume in terms of x. So the volume of a rectangular prism is length by width by height. So the length is 24, take 2x. The width is 18, take 2x, and the height is x. So I've actually rewritten those, or written those slightly different order. There's the length, there's the width, and I put the height in front because that's the standard way of writing algebraic expressions like this. Now we're going to have to find the derivative of this. So if we left it in that form, we're going to have to use the product rule, which doesn't sound all that particularly nice. So what I'm going to suggest you do now is, just for a bit of practice, go ahead and expand that out completely. So I want this written in expanded form. Okay, hopefully you've had a go at that. So I prefer to expand out these brackets first, which has given me that. So if you've tried this yourself, you might want to just check my answer, then multiply that whole thing. Oh, first we then have to simplify it by adding or subtracting the like terms, and then we multiply through by x to get that. So this equation here, or this expression here, is much easier to differentiate than that one. Okay, step number 3, find the derivative. Well, that's pretty straightforward. 12x squared, take 168x plus 432. Okay, what we're going to do now is set the derivative equal to 0, like so. And we've now got to solve this equation for x, and it turns out that it doesn't factorize nicely. So what we did for this one is we used the quadratic formula. And once you do all the calculations for that using the quadratic formula, you get those two values. Oops, I better keep that there for now. You get those two values for x. Now, if you look at x equals 10.6, and you look at the width of this piece of tin, it's only 18 centimeters wide. You can't cut out a square from there and there. That's 10.6 centimeters on the side. So we can eliminate that answer. It doesn't fit the practical problem that we're trying to solve. So it looks like we found a turning point, or I should say a stationary point. X is 3.4 centimeters, rounded off to 1 decimal place. Okay, the next step is to use the second derivative test to find out if this is a max or a min. So the second derivative of that is just 24x, take 168, sub in 3.4, and the second derivative is negative 86.4. And that means we have actually found a maximum volume, which is what we were trying to find. And the actual volume is, if you plug that number back into the original volume formula, we found the volume of that function, the volume of that open box is to the nearest cubic centimeter, 655 cubic centimeters. Now the last thing we have to do is say, well, maybe the domain for this function, let me go back up and show you the whole piece of tin again. The domain for this function, x can be as small as 0, which means you basically don't cut out anything at all. I guess it really can't be 0 because you don't have a three-dimensional tin in that case. So x must be bigger than 0, and the biggest it could possibly be is 9, because 9 plus 9 means you got no tin left, basically. So effectively, you're basically saying that if x is 0, you've got no volume. If x is 9, you've got no volume. And therefore, that is the maximum value. And that is the maximum size of the square that we cut out, the side of the side of the square, size of the side of the square. And that is the final answer. So we're going to stop there for in this series of videos. There are plenty of optimization questions in both the Year 11 textbook and the Year 12 textbook, and plenty of optimization questions to be found online. And a lot of them can be quite difficult, but the technique for all of them is going to be much the same as this video. Okay, well, if you're still watching videos, thanks for watching all of these. And the secret now to success is go ahead and practice all of this stuff from questions in your textbook or questions you find online. Okay, goodbye.